Welcome back. Can you guys at the back hear me? Is it working? Okay, thank you. All right, today is going to be Formal Developments Day. I'm going to talk today about some aspects, not the full thing, some aspects of the renormalization and the renormalization group. And later on, I will talk about a further refinement of the classification of leading and subleading operators that we've been talking about. So without further ado, let me start with renormalization. The first thing I want to cover is the fact that the theory that I've been telling you, that the theory is renormalizable. The operators that I'm going to look at, again, have this general form. I changed a little bit the notation. You should get used to it. I will not apologize. Sometimes notation change, the meaning doesn't. I used to call the boson fields phi and the fermion fields psi. Here it's called B and F, or bosons and fermions. And D is a covariant derivative. Has a coefficient that has a number times a appropriate dimensional coefficient to ensure that the whole the product of C times O has dimensions 4. And in order to do that, then this delta has to have the dimension of the operator minus 4, which is specifically listed here. Okay. Okay. The statement that the effective Lagrangian is renormalizable. How do we go around proving it? You can consider any effect, you can regularize the theory by any means that you find convenient, like dimensional regularization. Okay, and so when you do any graph, dimensional regularization is not confined to theories that have vertices of dimensions 4 or less. It can be used for any theory. So you can imagine doing a calculation with any term involving any number of terms, either in the light theory or in the effective operators. Those are, because the effective operators are local, the vertices are the usual Feynman type vertices, except they may have many legs and they might have many powers of momentum inside. But in principle, you can do exactly the same calculations that you do in regular renormalization studies of renormalizable theories. Once you do that, you do a calculation, you find that the graphs that you evaluate when dimensionally regularized appear with poles of 1 over dimension minus 4. Could be to one loop, you will have, and I'm going to call that quantity dimension minus 4 epsilon. So you have poles in epsilon, have factors of 1 over epsilon. In one loop, you get 1 over epsilon. In higher loops, you get higher powers. But the point that I want to make is that the coefficient of this 1 over epsilon or 1 over epsilon squared of all the poles are always polynomials in the external momentum. There's never a logarithm multiplying a 1 over epsilon. There is never some rational function of the momenta. It's always a polynomial of the external momentum. And so the divergences are associated with this thing. And second, the theory, the full theory, and I've been insisting on this, satisfies all the local symmetries of the light theory. And so you have, and this is respected by dimensional regularization. That's its virtue, that it respects the local symmetries. And so you have a theory where the divergences are, as in the one examples that you've been looking at in your career, they're polynomial in the external momenta. The divergences obey the symmetries. And what I mean here is that divergent terms, regularized, obey the symmetries. So you have an expression that has a 1 over epsilon or whatever, 1 over epsilon squared or whatever, multiplied by a power of momentum corresponding to a graph. And this exact vertex, power of momentum thing, corresponds to an operator. Yes?
These operators
Can be a higher dimensional operator.
and redundant operators.
And can be a redundant operator, absolutely. Actually, if you actually work it out, the redundant operators really take care of themselves, but I will not go into that. It's a detail. But it absolutely could be a redundant operator. It just shows up as an. Okay, and therefore, because the divergence satisfies the symmetries and corresponds to an operator, divergence can be absorbed in one of the infinite number of coefficients that I have. Because I've listed them all. I have a divergence that corresponds to an operator that satisfies the symmetries, and therefore it must be in my list of operators. It must correspond to one of the COs, and therefore the divergence can be absorbed in redefining that particular CO. And that, since I haven't specified what kind of graph, will occur to every graph that has a divergence. And this simple argument shows that the theory is renormalizable. All the divergences correspond to a local operator that satisfies the symmetries, and therefore it's in the list. So, as I mentioned much earlier, then the issue is not renormalizability. The theory is renormalizable. The problem is that we have very many coefficients, and so one needs to be able to do that, to deal with that, if the theory has any predictability at all. Renormalizability is not an issue. You don't have to use dimensional regularization if you don't like, but what is really, really, really useful is to ensure that the regulator, whatever it is, respects the local symmetries. If your regularization breaks the local symmetries, then doing renormalization that way is awful. I mean, it's really awful. It's difficult. There are books that do that. There's early books by Bogolyubov and Shurkov. It's a very old book, like the 1960s book. They do that. They renormalize QED, in fact, with I think it was a cutoff, which doesn't respect the local symmetries. And the results are very complicated, unnecessarily so. But there is still a renormalization question. And this is the following question. Could it be that operators high in the hierarchy renormalize those lower in the hierarchy? You might say, well, it doesn't matter. It's still a renormalization effect. But it matters if for some reason you are interested in calculating the renormalization group running of the coefficients. Because if you do that, if this does happen, and you want to calculate how a low-dimensional operator coefficient runs, you will find that because of this feed down from higher dimensional operators, for example, in the weakly coupled case, to lower dimensional operators, that the running of the low dimensional coefficients depends on the high dimensional coefficients. And in principle will depend with a high dimension of any dimension. So this thing would imply the running equation cannot be calculated, cannot be measured in a way, because the precision to which you can measure coefficients ends at sufficiently high level, and so these guys will eventually become unavailable to you. You cannot measure them, not because the coefficients themselves are small, but because lambda is large. Lambda, capital lambda. The scale is very large. So the effects of these guys, the high dimension, is unobservable because of limited experimental precision and because the capital lambda, the scale of new physics, is very large. But these coefficients can all be of order 1. And so if you do that, then the right-hand side of the RG equation cannot be determined, and the running itself is unavailable to you. That would be very unhappy situation. Really lack of predictability, because then the way the coefficients behave depends on quantities that are not acceptable for you to measure. So, if we're going to have a hierarchy, this better not happen. And let's see if that's true or not. In fact, you might expect it will be true. I mean, it doesn't happen. This really doesn't happen. So let me go back to a type of graphs that has a bunch of loops. Each of the 5 vertices here is produced by one operator, O sub v, where little v is 1, 2, 3, 4, 5. And from this, you can calculate its naive degree of divergence. This is a straightforward calculation. And you get expression here, which can be expressed in terms of the dimensionality of the vertices, of the operators generating the vertices, and the dimensionality of the operator, these guys renormalize. And if you're wondering about these little slashes here, what I mean by this is that these external lines have been amputated. So there's no propagators here, just to. So this vertex 4 has 1, 2, 3, 4, 5 legs. 3 of those are internal, 2 are external, but they don't have propagators attached to them. I can rewrite the degree of divergence in terms of my indices. Now, of course, n divergence doesn't depend on any parameter. Well, on this arbitrary parameter u I introduced before in this thing. But if you actually write this out, you find that the u dependence cancels out. All right. So each OV has it gives, in a sense, a factor delta V, and you have this relationship again. Okay. Now, the naive degree of divergence is associated with the leading divergence in a graph. So typically, you get a factor of the cutoff to the power n divergence. That's what you do when you do this. In dimensional regularization, you don't get. I know you don't get you don't get cutoffs, but you can make a correspondence between the powers of 1 over epsilon and powers or logarithmic dependence on the cutoff in a standard way. That's a standard renormalization parallel that one can derive. If I want to obtain the group, I need to find out more details about the divergences. So I'm going to be talking for the next few minutes about infinities. Now, if we go and look at this expression here, if u is less than 4, or equal, less or equal than 4, as I will assume, and all these guys are positive, all these indices are positive, this quantity here is positive. And so if you have a divergent graph, this object is greater or equal than 0. I'm going to write on the board I can quickly here. And div equal to 4 minus u. L, I forgot to say, I'm sorry, is the number of loops plus the sum of S O sub V minus SO. And for a divergent graph, this is greater or equal than 0. I've assumed this is positive. This is positive. So when 4 is greater than u, and if SOV is positive, then you have that this guy four minus UL plus the sum SOV is greater equal than SO. The index of, so these are the vertices, and this is the operator being renormalized. Okay? We have those relations. Very simple. So, if this is true, then each of these guys will be greater than this guy. I'm sorry. If for divergent graphs you have this, then operators that can renormalize with lower, that can renormalize O, these guys renormalize O only if they have lower indices. But indices are positive. So if this is positive, then I cannot have any of these guys be larger than this because this inequality would be violated. You know, I cannot have this. So let me just go by this carefully. So if the indices are positive and 4 minus u is positive, then this equation holds. SA is greater than SO. That's it follows from the previous expressions, from this. And so operators, the OA, renormalize operators with lower or equal index. That's what it means, provided this is true. And so in that case, the U is consistent. And so the question reduces to, that is, you will never get this. This just doesn't happen, provided the index is positive in this region, 4 greater or equal to u. It reduces to saying whether my index is positive or not. And it turns out, from the previous expressions, very straightforward, that this is true. That the index is positive, provided this is positive. And this is true, provided the dimension of the operator is at least 4. So everything holds out nicely, provided I don't have dimension 3 vertices in my theory. These are super renormalizable operators. And the reason they are problematic is that in the spirit of effective theories, all coefficients, all dimensional coefficients in the effective theory, well, they're associated with the scale lambda. And so you might think that these operators that have dimension 3 will have a factor of lambda, not the power of 1 over lambda, but a factor of lambda in front. And so every time you insert or you have one of these guys appearing in a graph, it gives you a positive power of lambda and therefore screws up the counting in the sense that lower dimensional operators contribute in the wrong direction for finding in generating the renormalization group running. So these guys require extra care that I will go to in a minute. So if you have 0 naive degree of divergence, that means the divergence is logarithmic, and the renormalization group running is generated by it and has this typical form. This is from the estimates that I've been doing earlier, like the one I did yesterday, and this is just dimensional analysis that one gets. However, if the naive degree of divergence is positive, then the renormalization group running is not generated by the leading divergence in the graph, but in fact by a logarithmic subdivergence in the graph. And because it's a subdivergence, it appears with a factor of this sort. So you get this guy, and then you get a suppression factor of a light mass over lambda times n divergence times the power of lambda. These type of effects I would call sublinic because they are suppressed by a small scale over the large scale of new physics. So we were interested really in graphs that have naive degree of divergence equal to 0. The other ones provide sublinic effects. So this is what this says. When this occurs, this is true. This is basically this is dimension of OV minus 4, and this is the dimension of O. Okay? And so the issue in this language of the deltas with super renormalizable vertices is that this delta, which is dimension of the operator minus 4, is positive except for this super renormalizable vertices of dimension 3 for which the delta is equal to minus 1. However, if you have a super renormalizable vertex which has a factor of lambda in front, not any other scale, but lambda in front, then you have a problem. Let me illustrate that with a simple model, with a scalar model. So suppose you have a scalar model with a quartic potential and you also have a super renormalizable vertex of order with scale of order capital lambda. Let me put a minus sign here, it doesn't matter. So how does the potential look? This is the potential. Well, minus the potential. If you have no lambda, no capital lambda, no super renormalizable vertex, the potential is nicely of a nice parabolic shape. Like that. So this is the case of lambda equal to 0. And here, the potential is approximately 1/2 m phi squared. This is a function of phi. This is v. No problem. If you have a potential term that goes like phi cubed, things change because, or necessarily change, because lambda is very large compared to m. So in that case, the phi cubed term is positive. I'm going to kind of make a dot line here, and negative for negative size. And this drop is steep because lambda is very large. So what you get is a rather steeper behavior on this side, but here you get a dip. Produced by the cubic term. Eventually, the quartic term wins out, and so you don't have a problem with having no vacuum. The thing really goes to infinity on both sides. But in between, you have a minimum that is not at 0, and you can calculate what the mass would be around here, around that minimum. That is the curvature of this. The curvature is of order lambda. So if you have a large cubic term, two things happen. You get automatic spontaneous symmetry breaking. The vacuum is not here, as it used to be here, but it's here, because this is lower. That's a vacuum, at least in perturbation theory. And the modes around the vacuum are heavy. How heavy? Very heavy. In fact, I'm telling you that the modes that we don't talk about are those that have energies, masses of order lambda or higher. So once you put in this thing like this, you've automatically, even if it doesn't look like it, you've actually turned the mass of your phi field into one of order lambda, not of order m, as this seems to indicate. Even though this has higher powers and blah, blah, it doesn't matter. And so adding such a term eliminates the phi from the low energy theory. So these guys, if you have any field that has a cubic term like this, it is not in the low theory. You don't have to talk about it. Now that doesn't mean that you cannot put any cubic terms in your theory. You can, if you should. But the scale that you put here must be much lower than lambda for consistency. So this scale, in fact, should not be lambda, should be smaller scale. When you do that, then everything works out fine. Why? Because any type of renormalization effect that includes these guys, the cubic terms, now instead of lambda has a small scale, and therefore the renormalization effects actually look like this. And therefore they are subleading because the vertex explicitly has a small scale in front of it. It follows this rule. It will be then subleading, and we're back to a situation where only operators with delta positive give you the leading running of the coefficients. And if you go back to my slides, which I'm hesitant to do at the moment, this corresponds to the case of only lower dimensional operators renormalizing higher dimensional ones, or lower guys in the hierarchy renormalizing ones higher up in the hierarchy, as opposed to the other way around, which would be problematic. So in all, the final result is this hierarchy using the indices that I've introduced is consistent with the loop expansion in the sense that I mentioned, that the renormalization of the operators is from leading to subleading and not the other way around. So in terms of the index SO, the guy being renormalized has an index that's larger than the ones in the graph, and so it is these guys that are leading because they have lower index. They're leading that renormalize guys with higher S, which are subleading. Okay, so these guys, what does not happen is that the guy with a large index, subleading, renormalizes operators with lower index to leading order. And so when you write down the effective theory, you can classify it according to the terms that have indices that are, small, larger, 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 larger in groups of the same index, and it's the guys in one group with low s will renormalize with high s, but not the other way around. So LS renormalizes, the evolution of LS is generated by guys below it, but not the other way around. And so if you do standard model plus dimension 6 operators, in fact, all this thing doesn't show up because there's no cubic terms there. So standard model plus dimension 6 operators, then in a way that's a closed system. You can find the evolution, the leading evolution of the coefficients, all the coefficients, standard model and effective ones, using that closed set of operators. You don't have to worry about dimension 8 operators. Yeah. Dimension operators, the 8 operators will produce subleading corrections. That is, those suppressed by light mass over lambda to some power. Actually, in this case, 2 powers for dimension 8 operators. 1 power for dimension 7 operators. Well, actually, dimension 7 operators might occur twice. Well, it's always at least light mass over capital lambda squared or higher. And that's a very small number. Okay, so this is the thing about this renormalization thing. Now let me comment a little bit whether you actually want to do this. You actually want to go through the effort. I just argued that this doesn't show up, so you just have this type of thing. Instead of having zero dimensions, have zero to some power, right? Some power of these guys up here on the right-hand side. It gives you the running of this guy. This doesn't show up. That's what I've been arguing. But the question is whether you should actually do the calculation. And I want to argue that, in fact, you don't. I've just gone through this to show that the hierarchy imposed by the indices is consistent with the loop expansion. That was the goal. But whether you should actually calculate the running, I'm not sure that's worth the effort. Within the context I'm talking. Let me explain why. If you look at the measurements that we have done today, so far today, we are sensitive to a few one-loop effects within the standard model. We are beginning to be sensitive to a very select number of two-loop effects. Renormalization group is a loop effect. Running is a loop effect. So now I'm asking you to consider, you would ask yourself to consider what are loop corrections to the effective theory. And these are effects that are not going to be probed in the near future, right? Or in fact, in the not so near future, because they're very small. They are loop effects, which is a problem to begin with, in the sense that they're small. They have an inherent suppression. And on top of that, it involves effective operators. So they have an added suppression of the inverse powers of lambda. So that is a very, very small effect that we will not be probing for a very, very long time. And so for the moment, I don't think that particular calculation is very useful. It would be nice, it was nice, in fact, it was done, to show that this argument that I've been hand-waving about, that these terms don't show up, actually is realized when you do it, you actually do the calculation. People have done this. So it's an exercise that you solve whether the results are of great interest phenomenologically is more questionable. Now there's another approach where this is actually not true. You can imagine knowing the underlying theory. You know what is called the ultraviolet completion of the standard model. That means new physics. You know the new physics. And so at some scale, you would be able to see all this, new world. It's right here, the new world. You know it. You know what it is. You know it here. It's, it depends. If you're in the 1980s, it's a grand unified theory. It's right here. Okay? And here you have the standard model. And in between, you have the effective theory. The effective theory can be made to work all the way almost to the scale of the heavy guys. But not beyond. Okay? So what you can do is say, okay, I don't want to deal with a grand unified theory. I just want to deal with my standard model effective theory. So I can match the true theory to the effective theory at a scale that of my choosing. So I can say, what do I mean matching? Well, you calculate a bunch of observables using the effective theory, and you calculate the same observables using the full theory, and you make sure that the results match. That's what it's called matching. In the process, the coefficients of the effective operators are expressed in terms of the parameters of the underlying theory. They're no longer arbitrary. They depend on the parameters of the full theory that explains the universe. Very nice. Why would you want to do that? Well, maybe effective theory is more convenient. Maybe nobody has written the right MAD graph files for the grand unified theory that you know is true, but everybody has written them for the effective theory that's below. Maybe just a practical thing, that kind of thing. All right, you can match them at any given scale. You can match them almost at the grand unified scale, or you can match them below. If you match them at a very high scale, grand unified scales are large, 10 to the 16 GeVs and so on. Our experiments are 10 to the 3 GeV. So if you match them here, you really want to do the evolution of the coefficients. Now, this is the effective coefficients from that very high scale to the LHC scale. You really want to do that because the energy gap is humongous, right? Okay, so that in that case, doing the running is very useful. You match at the high scale and you run the coefficients to the scale of interest to experiments. And that's fine. You could also match at the LHC scale. That's also possible. Fine. Okay. In which case, doing the running, it's not very useful. If you match at 3 TeV, LHC is at 1 TeV, you know, doesn't move. This effect, the changes of induced by running are very small, unobservable. So, but in that case, if you match at a very high scale, it is useful to know how the coefficients run. But that is a very specific situation. I'm telling you, you already know how the universe looks. The question of what is under the standard model has been answered. And, you know, doing an effective theory, which is designed to talk about situations when we do not know the underlying theory, you know, it kind of loses interest. We already know the underlying theory in this scenario. And so you might imagine situations where the underlying theory becomes apparent at a very high scale, in which case then the running from low scale to that very high scale it will be significant. On the other hand, since you don't know what's beyond that very high scale, I mean, you just run the coefficients and you just finish. You know, there's no physical content there. And so the running of these guys within the EFT is not very interesting because the effects are small. The running becomes interesting when you go from this top-down approach in that case. But in that case, you have much more interesting things to do. That is, understand the underlying theory, which is the true expression of nature, not the EFT. Any questions?
So,
Yes?
so in one of your slides, you have written SO8. So is it same as SO8?
SO8, yes. I'm sorry. A and V are the same index. Sorry. It just I used to label the vertices, and I changed. I apologize. Sorry. Yes. Sorry. Other questions? Okay. So again, this exercise was made to show that the EFT is compatible with the loop expansion, but disappointingly perhaps, I've also argued that doing the calculation is not as interesting as one might hope. Since I have a few more minutes, let me begin with the next topic, which is much more useful. Much more useful. I've been arguing, and this is much more useful for the case where the underlying physics is weakly coupled. I've been arguing that in that case, the appropriate expansion, as expressed by the index S, will be in powers of 1 over lambda. Large power, small effect. Small power, larger effect. But in fact, we can refine that. We can refine that. Because some of the operators, as I will argue, some of the operators that you face are necessarily loop generated. So the coefficient that is independent of the type of new physics that, well, I'll qualify that. If the new physics is a version, completely arbitrary version of a gauge theory, that is a theory composed of fermion scalars and vector bosons, but without any further specification, then there is a group of operators that are always generated by loops. They cannot be generated at the tree level. And that is important phenomenologically because the coefficients of such operators are then suppressed compared to the coefficients of other operators. And so those operators have small effects in themselves. And so you want to look at them, fine, but you have to be aware that the effects that they produce are going to be suppressed compared to the effects of other operators. Unfortunately, many of the very interesting operators, those that produce could produce significant deviations from the standard model, are the ones that are generated by loops. And though it might look at first sight that they generate significant deviations, they do not because of the operator itself, but because its coefficients necessarily have a extra suppression factor beyond the power of the scale. And that's what I'm going to talk about today in a minute, in the following. Oops. Okay, so let me make a definition. Oh, okay, so this is the kind of thing. So let me make a definition. Suppose you have an operator that's generated at tree level. Then the coefficient by some underlying weakly coupled decoupling underlying new physics. The coefficient then will be expressed in terms of the coefficients of the underlying theory by an expression of this form. If the operator is generated at the loops, you have a similar form, except there is a suppression factor, which, as I mentioned here, is so strong that makes the effects of this type of operators unobservable. My point is that these guys are phenomenologically more interesting than these guys in most situations. There are exceptions, and I'll mention one, but in most situations, this is the thing. These guys provide the best window into new physics available to us. Here I assume, as I mentioned earlier, that the standard model extension that is the underlying physics, is a gauge theory. Beyond that, and it's a field theory, okay, that has local interaction. Beyond that, I will make no assumptions. Then I will argue that there's a set of operators that are always loop generated, always. And I will call them loop generated. The remaining operators may or may not be generated at tree level. So that means that there's certain kinds of new physics where these remaining operators are in fact generated at tree level, and there's other kinds of new physics where they are not generated at tree level. And I will give examples of this possible duality also in a minute. Since they may be at tree level, I call them PTG operators, potentially tree generated. To find these guys, I will need the allowed vertices. So I am going to assume the underlying theory is some gauge theory with a bunch of scalars and vectors and fermions, okay, completely general, that contains a standard model. Okay. And I am going to look at the tree-level graphs. This will be a constructive proof. In doing so, I will assume that there are no mixings between heavy and light fields. That is, there's no term in the Lagrangian that are quadratic in the mixing. What I mean is there is no heavy scalar times light scalar term in the Lagrangian. There is no light fermion times heavy fermion in the Lagrangian. If you have those things, the problem is that the mass terms are then mixed. Right? If you have I will do this as an example for for scalars. So suppose you have a scalar little phi that you say is light, and a scalar big phi that you say is heavy. Well, by this you mean roughly, and I don't want to be as very careful, that the Lagrangian has terms that goes like little m phi squared, big M phi squared, and that little m is much greater than big M. But if I add a mixing term, okay? Yes. Thank you. Other way around. Thank you. But if you add a mixing term, this thing becomes now more murky. If you want to identify what the heavy modes and what the light modes are, you must diagonalize the mass matrix. The mass matrix is m squared, mu squared. That's the mass matrix, right? And you want to diagonalize it. It will have, in general, a light mode that is a large eigenvalue or an eigenvalue much larger than the other one, following this hierarchy. But the eigenvector corresponding to the light and heavy will not be pure phi, will not be pure capital Phi, will be a mix of those two. And so it will be a mix of this and this that will be the light one, and the orthogonal mix will be the heavy one. I mean, that's fine, you just do it, kind of thing. But when I say there's light modes and there's heavy modes, I'm assuming I already did that. And so I can tell you ab initio, these are the light modes. If I had, for some reason, some mixing term, I already diagonalized my mass matrix. I already identified who's light and who's heavy, and then I'm done. There will be no such terms. Not in the sense that there will be no terms because they're forbidden. It's because I already dealt with them by diagonalizing this matrix, identifying what's heavy and what's light. So these terms are not there. Again, let me emphasize, not because they are forbidden, but because I eliminated them by taking appropriate combinations of the fields. And I need to take those appropriate combinations in order to identify what's heavy and what's light. Otherwise, I don't know. Otherwise, the phi that I call light, in fact, has a component of a heavy field. It's no longer light. So this is what I mean by this light column. Exactly. Yeah, exactly. So what I'm trying to say is when I say there are light modes and there are heavy modes, I mean there are light modes and heavy modes, and at least at tree level or at the very basic non-interacting level, I already ensure that's the case. There's no ambiguity in it. Okay? By diagonalizing all mass matrices.
Just making this making a square, so combination of a small 5 and 10.
Yes, exactly. Yeah, and so there's some linear combination of little guy and big guy that will have a small mass, and another combination, the orthogonal one, that will have a heavy mass. Okay. And so that's good. All right. So now,
We have some time.
I have 9 minutes.
Yeah, exactly.
Are you bored?
No.
Are you bored? There, I think I have some cartoons in the following.
Oh.
Okay, so, okay, I think, right. Let me just set up the notation and then we'll stop because it's been a heavy load for the moment. I think. The reason I don't want to just completely stop is I do have some phenomenological applications for tomorrow. So today is mostly formal and they're very much crammed into a lecture, and I want to have a little bit more time also. So I want to not stop completely now, so I'll have a little bit more time later. Okay. All right. Since I told you that the underlying theory, which is weakly coupled, is a gauge theory, it will have gauge fields. The full theory, gauge fields, I call V. And it's composed of two types of gauge fields, the light guys that I call A, and the heavy guys I called X. Okay? V is all of them, light and heavy. And the Lagrangian contains a kinetic and interaction term of the V's of this form, as any gauge theory does, where V nu A is the standard field strength tensor. There are some generators associated with the adjoint representation of the gauge group, which I call TL, T1, 2, 3, 4, 5. These are the generators of the group, or the members of the algebra of the group. Now, inside this group, the standard model group must be. There must be a subgroup of the full group, whatever it is, where the standard model group lives. In all grand, you can check that in all grand unified theories, you can find a subgroup that's SU2 cross SU3 cross U1. Always, always, always. I'm not assuming that the full group is simple. That is, it's not like SU10, SO10 or SU5 necessarily. It can be something else. It can be whatever the SU4 times SU4 or something like that. It doesn't have to be a simple group. It can be any group, kind of thing. But somehow inside it, there must be some combination of generators that correspond to the standard model gauge group. Those close into a subalgebra because it is a group inside the other group. And so the commutator of two of those corresponding to the light gauge bosons, which are the standard model gauge bosons, would be the standard model guys. The generators associated with the A, that I call light generators, must close into a subalgebra. So the commutator of two of them must give you another of them. This is not to represent an index. It just said the commutator of a light with a light gives you a linear combination of light guys. They will not give you any terms that have heavy guys. Another way of saying it is that the structure constant of the group that contains two light indices never have a heavy index beyond. So you can have an F with 3 light indices. You can have an F with 1 light index and 2 heavy ones. You can have a structure constant with 3 heavy ones, but you cannot have 2 light and 1 heavy. It just doesn't happen because of this condition that the light generators close into a subalgebra. And so based on this, I can find out from all the terms that show up here, which are allowed which are not allowed. You're not supposed to remember this. Trust me, this is correct. So the cubic vertices are proportional to the structure constant. The quartic vertices are proportional to a contracted product of two structure constant. And you can see from what I just mentioned here that these quartic vertices are allowed. Others are not. In particular, you see no vertex that AAX. There's no vertex like that. In fact, you can see it, and so in that, in fact, will turn out to be useful. And this implies, in particular, that certain pure gauge operators that made out of pure gauge fields are necessarily loop generated. This is the term in the Lagrangian that generates cubic terms in the gauge fields at tree level. There's no other one. This is it. Okay. And so you have if you have an operator like this that has three light generators, we will see later on that it's necessarily loop generated. We will see in a minute. Okay. Let me tell you, since I'm about to run out of time, let me tell you what's going to happen in a little bit, okay? I'm going to use this argument such as this, just looking at the structure, general structure of the underlying theory to find what vertices are allowed, not only in this type of terms in the Lagrangian, but also in those involving scalars and fermions. So you will see down the line lists like this involving scalars, involving vectors, here involving vectors, but later on involving scalars and fermions, which those that are allowed, those that are forbidden. And from those, since I know now the vertices that are allowed, I can check which ones actually can, I know the vertices that are allowed. I can find out what graphs, what tree-level graphs occur, and from those, I will find out which operators are generated at tree level. So it's involved, and it's formal, but I think it's a useful exercise to at least see it done once, even though it's not in full detail. Okay? I'll see you in the afternoon, where I'll complete the proof. Thank you. Again, I can't.
Only and one light index. Why it is not there? I mean, in your list of two.
Oh, why don't I have light? Yeah, light.
Light.
Okay. The reason that happens is I'm going to write on the board. Okay. So the question is, again, why no light guy? Explicitly is the following. Okay. So you have the general V mu nu. I'm not going to write in full detail. Okay, but looks like a derivative term plus a term with f and two v's, like this. All right. So this has an index A, here's A, B, C, B, C. I'm not going to worry about the Lorentz indices at all, okay? So I'm going to take the Lagrangian has a square of this guy, okay? So V squared, V mu nu, has several terms. Has the quadratic term, roughly, okay? Has the cubic term, and has a quartic term. Same A, C, D, E. Okay? Okay, I'm just took the square of this, and this, and I'm not worrying about factors of 2 or anything like that. Okay, because you don't have, because the light generators close into an algebra, what it means is that in general you have this expression, TA, TB, and I'm taking them Hermitian here, it's I, F, ABC, TC. This is for general indices. Now, because they close into an algebra, the light generators, T, A, L for light, and T light T1, light 2. Okay, these guys are some of these guys. Some of the TAs are the light generators. So for those you have I, F, L1, L2. I'm just doing C, DC, the general case. But because they close into a subalgebra, the commutator will necessarily be a linear combination of the light guys only. Okay, so it's I, F, L1, L2, L3, T, L3. There's no heavy guys here because they're close into an algebra. And so you can see that if you had a term that was AAX, okay, you have AAX or AAX. Two indices are light indices because the A's are the light guys, and the other one would have to be heavy. But that never happens. You only have light, light, light. You never have light, light, heavy. And that is you never get AAX or AAX or XAA. It doesn't happen. Okay? Other question? Okay. All right. Then we can go to T. Thank you.